Friday, right?
The assignment something Wednesday is what I heard.
The assignment that was due tonight is due Wednesday, right?
No. It's due tonight? Yeah. I made the one that was due Friday. I gave people extra time because some people said that because of family coming, they wouldn't be able to get it done. Okay, see, Alexis just got here and Jaron just got here. Okay, so to follow up in case there was any other confusion for what Zach said, on Friday I told you that I would allow you to turn in the assignment that was due on Friday on Monday. So today, Monday, we have the assignment that was originally due on Friday, has to be completed by tonight. The assignment from Friday is due tonight, and the Flip Friday for the handful who didn't get it done in class is also due tonight. So you have those three things that are due tonight. I was at least pleased that most of the people finished the Flip Friday in class this time. It's getting better as far as that goes. There was something else I was going to say. My mind being a sieve, things go through. I tried to grade some Flip Friday stuff, but we had a lot of things going on in our household yesterday, and I only got like 4 of them graded in the day. And that's even with the Raider game not on TV, so I didn't watch that. I was grading during the Raider game. Finishing just a few ideas from the last chapter. On Friday, for your Flip Friday, you were looking at energy, resources, and power. And so one of the equations that you learned on Friday was about power. So I have found, even when I lecture on it rather than students doing the self-guided learning, power gets forgotten very quickly. So I want to make sure I reiterate, what is power? So I'm asking you first and then get an answer, and then we're going to have a clicker question on it as well, I think. So I think that's what the first question has to do with. What is power, friends?
Work per time?
Okay, power is, let me write it this way first. Rate at which work is done. Which mathematically turns out to be exactly what you guys said. I don't want you to think I was saying you were wrong. That's the work over the time it took to do the work. So if you do work faster, that's a higher power. Do it slower, it's a lower power. Now work, according to the work-energy relation, we have the net work is the change in kinetic energy, or the work non-conservative is the change in overall energy. It turns out that power, the rate at which work is oftentimes just going to be change in some type of energy over time. Since work is change in energy, that also is accurate. So anytime we're talking about power, we have the change in energy or the work done over the time it takes. Now, for the units then, power has units of energy divided by time. Energy is joules, time is seconds. So the units of power are joules per second, which is commonly called a watt. Now, there are other units, for instance, horsepower. Horsepower is supposed to be, in theory, the power that a horse can produce. So it's the energy per time a horse can produce. And the conversion, since we looked at it this morning, is 1 horsepower is equal to 745.7 watts. I was going to put joules per second, but let's just put watts. At least if Michael looked it up correctly. And I'm trusting it. Now with this unit watt, that's where it becomes tricky keeping your units and your variables straight. Because if I use W for a variable, I mean work. Our textbook could mean either work or weight, because they use W for weight as well. If you have W for a unit, that's always going to be the unit of power, watts. So you have to be aware of this and not just look at a W and say, oh, W, and go with an answer. Make sure you know, is that a unit or is it a variable? One last thing before I go to my first actual slide here. How many people here have ever read Marilyn Vos Savant? She used to have an article, I don't know if she still does, in the Sunday version of our newspaper. It's called Ask Marilyn. I tended to call it Ask Miss Smarty Pants. At least one person has heard of her. Okay, couple. She gets asked questions over random things. She had, at least when I was in graduate school, the highest measured IQ on record. So, and her husband is the person who invented the Jarvik heart. Ever heard of the Jarvik heart, an artificial heart? Okay, so she gets asked these random questions, and she's supposed to show her, wisdom of Solomon or whatever in answering them. And one of them that cracked me up was this one here. You have 2 bags of groceries, and you live on the 2nd floor of your building. So, whoops. So basically, here's the ground floor, and then you have stairs to get up to the 2nd floor. And you have 2 bags of groceries. And the question was, which requires less work? Oh, wait. You live on the 3rd floor. There's a landing in between. I've got to get this straight. This is something she wrote back when I was in graduate school that made me laugh back then. So, okay, so you live up here. So which is less work? And the 2 options were, and I will put the first option in green. You take 1 bag. Oh, there's one last caveat. You're not strong enough to carry 2 bags at one time. You only carry 1 at once. So option 1 is to take a bag, come up here and set it down, come back down, get another bag, come up here, then take a bag up to the top, come back down, get the other bag, and take it up to the top. So you took a bag up to the first flight, set it down, went back down to the bottom, picked up the second bag, took it up to the top of the first one. Then you took a bag from there to the top of the 2nd flight of stairs, set it down, went back to the middle, picked up the other bag, and took it to the top. Clear enough? Okay, so that was option 1. Option 2 that I'll show in blue, option 2 was to take a bag all the way to the top and set it down, come all the way back to the bottom, take the second bag, and bring it all the way up to the top. So, which requires less work? Oftentimes I do this with a clicker question, but I didn't do it today. There are 3 possible answers. 1 is less work, 2 is less work, or they are equal. So, A, 1 is less work. B, 2 is less work. And C, they are equal. So let's just, because I don't have a clicker thing here, I know it's nicer to be anonymous so you don't have to have people look at you and say, oh, what? How many people, by a show of hands, think number 1 is correct? It's less work, or A is correct, it's less work to take 1 bag to the first landing, go back down, take the second one to the first landing, then go to the second landing, come back to the first landing, go second landing. How many people think that's the least amount of work? Show of hands. Okay, so that is 0, according to you. Okay, how many people say number 2, taking 1 bag all the way to the top, going all the way back down, second bag all the way to the top, is less work? So I've got 1, 2, 3, 4, 5. And how many say C, that they're equal? Very large number. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that was 17, which is pretty good. That's, I think, everyone that's here. I may have missed one person. There might be one more person here. So we've got a good, clear consensus here. This one here is the one that had the biggest vote. Now, Marilyn answered, and obviously this sticks with me because of her answer. She answered this one. She said setting one down in the middle, going back down, that's less work. Now, I can think of lots of ways to explain this, and I could honestly answer either B or C is correct. But there is no way in God's green earth that one was the correct answer, and that's the one she chose. And so, well, let's see, why would B be correct? That is going all the way to the top, all the way back down. Because if you're talking the energy that your body is consuming, having to set down and pick up is extra work that your body has to do. In terms of mechanical energy, you set it down, pick it up, that's a net work of 0. But in terms of your body, you don't get energy when you set it down. So for your body, that was extra work. So actually, 2 is less work is a perfectly acceptable answer if you're talking about the energy your body has to expend for your definition of work. C is correct if you're talking about mechanical energy, which is what we do in general physics. In general physics level, if we're just talking about mechanical energy, it's the same because you're just working against gravity and you had the same change in potential energy in both cases, hence the same work done against gravity. Her reasoning for answering this was, you feel less tired. Now, many of us have gone to the gym. I did this morning. Whether I work out for a half hour or an hour, what really makes me feel tired is not how much work I did. It's how hard I was hitting it. Right? If I was, let's say I'm on the treadmill, God forbid, ever since my pulmonary emboli, I haven't been able to run. But if I was on the treadmill going as fast as I could, I would be really, really tired. Whereas if I was just walking, I wouldn't be as tired, right? So I could walk a mile over the course of an hour, or I could run a half mile over the course of 5 minutes. I'm going to feel more tired after the half mile in 5 minutes than I would a mile in an hour. But which one would be more work? The mile would be more work. What she was answering was really the power. That is the work per time. If you're going up to the middle landing, set it down, going back down, you're making it so it takes longer to do the work. And by making it take longer, you're not going to feel as tired when you're done. So she showed a fundamental failure in understanding what these physics terms are, and thus I laughed at her. Miss Smarty Pants was wrong. We physicists know better. Because, we all like to be smarter than somebody at some point in our life. Okay, so a related question to test our understanding of work. Rich and Ron's my little brother, are each given 1 ton of beans to move from the back of a truck into the storage room in the barn. I've made up the numbers. I don't know how long it would take me to shovel a ton of beans. Probably a long time. No. Anyway, moving on. Rich starts immediately and finishes 1 hour later, because that's the kind of guy Rich is. Get the job done. Ron waits 3.5 hours, because he was lazy, at least as a kid, before starting and completes his work after only 30 minutes of labor. Because the sad truth is my little brother is bigger and stronger than me. Which statements are true for the 4-hour time period? So notice it's for the entire 4-hour time period. And so there are multiple correct answers. Choose the 2 that you believe are correct, because obviously there can only be 2 here. And then hit enter.
Your hour is just 1 hour, or are we counting the 3 hours?
It's 4 hours in both cases.
Which time I was talking about average over the 4 hour time.
That's talking about the average over the 4-hour time.
Can we change it?
Just put in your answers and hit enter. And if there, I think there's a back here. You can just hit enter and then start over. Okay, so I got your second answer. Okay, still waiting on Sally and Toussaint. It's not answering? Okay, then in that case we had 3, 1, 18, 2, 9, 10. Now normally I would have you discuss it with the people next to you, but because of time, I will curtail that and go to having Chad answer. Chad answered because Chad had to change his answer, which means that, you know, he first had one idea and then he corrected it to another. I hope corrected it. So, in the first three, Chad, which did you choose?
C.
C. They did the same amount of work. That was the vast majority there. What logical reason could you have for that being the correct answer?
They both moved a ton of beans.
Both moved a ton of beans. So the work was the work to shovel those beans, did the same. Yes, that's correct. Now, for the second one, I'm still sticking with Chad because I have some confidence. And Chad's all, yeah, great. What did you answer for the second one?
First time or second time?
The time you thought it was correct.
F.
F, which had a plurality, no majority. Why did you choose F?
Because I realized that when you're talking average power over the 4 hours, that they still did a ton of beans per 4 hours. In the same 4 hour time span.
They both had the same work, and because I said over the 4 hours, the average power was the same. What was your first answer?
E.
Your first answer was E, that Ron had the higher average power. And why was that?
Because he did more work in a
Okay.
shorter time period. He did the same
His
work in
peak
short-
power, when he was working, he did all of that work in 30 minutes, whereas when I was working, I did all that work in an hour. So his peak power, his production when he was actually working was higher. And so you covered all the bases in your thought. First you thought about the peak power, the power when he's actually working, then you thought about the average over this time span. I had faith and it was well deserved. Any questions about that power-work relationship? No? Then let's talk about momentum. It would be accurate but unpleasant to say that the New England Patriots currently have a lot of momentum. What does this mean? And notice that multiple things here are correct answers, but only one is what this means. I'm looking for physics understanding. Okay, so we had we had a majority that said that this means that they are hard to beat. And when we're talking about sports, that's exactly what we mean when we say they've got a lot of momentum. They're going to be hard to beat. When something has a lot of momentum, it's going to be hard to stop. They are cheaters, I think, is pretty much an obvious truth. Don't need to go through all the instances where they were caught cheating. Or my unrest at seeing that Walt Coleman is still officiating after we got so blatantly jobbed. You know, they changed the rule on the tuck rule. And so, guy who used to work for the Raiders, Bruce Allen back then, asked for clarification and described the situation where they called the tuck rule and disallowed the fumble. And the guys from the NFL laughed and said, oh, that would have never been, a tuck rule. That would have always been a fumble. At which point Bruce Allen started fuming and they realized that they had just laughed and admitted that that had been a wrong interpretation. Okay, so moving on. Momentum means something's going to be hard to stop. That's what we think of it in a practical sense, and that is relevant to the physics definition. The physics definition is a simple mathematical definition. Momentum is mass times velocity. Looking up there, in case you didn't read and do the reading quiz, what symbol do we use for momentum? P. I honestly don't know why P is the symbol for momentum, so I can't give you something to even help you remember it other than P is momentum. I memorized it when I was in high school, and I still remember it, mostly because I've been doing physics ever since. Notice that it has a vector sign. Momentum is a vector. It's just the mass times velocity. So something that has more mass and is moving will have more momentum than something with the same mass, or the same speed but lower mass. Or if something is going faster, it'll have more momentum than something that's going slower with the same mass. So it's very simple: momentum, mass times velocity. Let's just do real quick calculations. Here I have the blue car that is traveling at 5 meters per second and has a mass of 500 kilograms. What is the momentum of the blue car equal to? Okay, it's going to be 500 kilograms times 5 meters per second to the right equals 2,500 kilogram meters per second to the right. To the right because it's a vector. Kilogram meters per second are the units because kilograms are the standard unit of mass, meters per second the standard unit of velocity. So that's not a very difficult calculation. It's kind of nice when our calculations aren't difficult because the ideas sometimes are more intense, and we need to spend our energy thinking about the ideas and not all on the calculation. Really quickly, what's the momentum of the yellow car? .800 kilogram meters per second to the right. Now, if it's one-dimensional motion, what have we used in the past to indicate to the right and to the left? Positive to the right and negative to the left. So very often I just would have said plus 800 and plus, and of course you don't need to write the plus, I'm just saying that for clarification, plus 2,500 kilogram meters per second. So that's what momentum is. Question?
Yeah, I feel like I should know this, but is momentum the first integral of force, considering...
Segueing into his question, Newton's second law. How many people here know Newton's second law by heart? Only one was willing to say. Okay, two.
Like the full thing, or just like the equation?
Yeah, just the equation.
Oh, yeah.
Newton's second law. Sum of forces equals mass times acceleration. Right? Of course, what's the definition of acceleration?
Change the velocity of the time.
Okay, so I'm going to put mass times change in velocity over change in time. Now, if, and this is only true if my statement is correct, if mass is constant, then m delta v is the same as delta parenthesis mv. But of course, what is mv? It's momentum. So I can also write Newton's second law as sum of the force vectors is equal to the change in momentum divided by the change in time. In truth, this is the correct form of Newton's second law. That if and only if statement actually applies to going to the law we learned. Only if mass is constant is this equation correct. But this equation is always correct. And now, since Chad had asked, this is truly a calculus equation. The true equation, the reason Newton invented calculus is because what it really is, and I'm going to use net here, net force is equal to the derivative of momentum with respect to time. Or you could say dP is equal to F net dt, and then you could integrate up and have your answer that P, well, it'd be delta P now, is equal to the integral of F net dt. That's what you were asking. So that last part was to answer Chad. I don't expect people in physics 151 to make sense out of that, but to make sure that I get an answer for Chad and don't leave him hanging. Much like, you guys are too young to remember the hanging Chad, aren't you? The presidential election that Al Gore lost and tried to sue in court to be president anyway. And I do believe Al Gore had the majority of the popular vote. But you should all know that we do not have a democracy in the United States. Everybody knows that, right? Not a democracy. What kind of system of government do we have? We have a democratic republic. We democratically elect the people who are going to make the decisions for us. So in our elections, what we're truly voting on is who's going to cast our vote for president. That's what we vote on in a presidential election. And that's what the whole electoral college is the people who got elected to cast votes for president. Okay, just make sure we've got that civics lesson in there. Let's move on. I think it's another clicker question. Yep. An 80-kilogram man and a 40-kilogram woman are on ice skates. If the 80-kilogram man carefully pushes, oops, it's supposed to be a 40-kilogram, not 50. 40-kilogram woman. So he ends up moving backward at 0.25 meters per second. What will happen to the woman? No, they're standing here, and then he goes.
Wait, is he holding on to it the whole time?
He's going to let go after he pushes, so he's not going to yank her back. Okay, we have all our answers in. Nobody said she'll move backward at 0.25 meters per second. One person said she'll move backward at 0.5 meters per second. 6 said she'll move forward at 0.25. 15 said she'll move forward at 0.5. 1 said she'll fall down, cry, and be very angry with the man for demonstrating physics. Okay, let's look at this. Any physics problem, I always start with the picture so we can understand what's going on. So here's the girl. We'll call her Naoko just for fun. And then we're going to have the man. Yes. We'll call him Richard just for fun. Yes, it's a true story. And one person got the answer right. So Richard gently pushes on Naoko. So there's the force. Now, according to Newton's second law, if Richard gently pushed on Naoko, what's going to happen as far as Naoko and Richard, the forces? Equal and opposite forces. So Nalco had to have pushed back on Richard with an equal and opposite force. And so if we look at this, I could say I'm going to set my system to be the system that includes both Richard and Nalco. So my system is going to be all of this, and all of this, the force net is equal to 0. Why 0? Because they're on ice skates, so there's going to be no friction in the forward and backward direction. And force of gravity is down, force normal is up. Those are going to add to 0 so they don't accelerate and hop up off the ice or sink through the ice. And then the forces between them are within the system. So the net force is 0. Well, according to Newton's second law, I drop the vector sign because I'm going one-dimensional. The net force is equal to change in momentum over change in time. So if the net force is 0, what does that tell you about the change in momentum? It must be 0. So in that case, we say, momentum is conserved. So anytime the net force on your system is 0, the momentum of that system is conserved. What does conserved mean in physics? That it's constant. It doesn't grow, it doesn't shrink, it stays constant. So the total momentum of my system is going to stay the same. So momentum is conserved means momentum initial equals momentum final. What were the velocities of Richard and Nalco here to begin with? V initial equals 0 for both. So momentum initial is equal to the mass of Nalco times the velocity of Nalco initial plus the mass of Richard times the velocity of Richard initial. That's equal to 0 plus 0. That was real simple. Momentum final. Momentum final for Richard was the mass of Richard times the velocity of Richard final. And we know the numbers for that. That's going to be my 80 kilograms times minus 0.25 meters per second. Why minus? Because I said backward. And I like to say backward is negative. Even though in my picture, I'm going to have to say positive is to the left to make backward be negative. But I just like saying backward is negative. So that's momentum final for Richard. Momentum final for Nalco. Mass of Nalco times velocity of Nalco final. If I put these into my equation for conservation of momentum, I will have, okay, I can't slide up so you can't read it and then write it. Momentum initial equals momentum final. 0 equals, and I will write it in variables. If I solve this for speed of Nalco final, the reason I didn't put the numbers in here but put symbols is because it becomes very simple. Mass of Richard divided by mass of Nalco, 80 divided by 40 is 2. And I forgot my minus sign because I'm bad at math some days. So this is just going to be equal to minus 80 kilograms over 40 kilograms times minus 0.25 meters per second, which comes out to be 0.50 meters per second. So she should end up going half a meter per second forward. And so here's a picture of what should have happened. Now these people are on roller skates because I didn't get any photographic evidence. If I had photographic evidence, I wouldn't show you anyway. And yes, here's what really happened. I carefully explained what I was going to do. She said, cool. And then, yeah, she fell. She cried a lot and was very angry with me. And it only got worse. I took off my skate and it was filled with blood. And I was like, ah, no, blister. Took off my sock. No blister. Yeah, they'd given me a boot that was filled with blood from somebody else who had had a blister. Yeah, that was an awesome, awesome day. Okay, so we worked through a problem with conservation of momentum. And conservation of momentum is very important, and we're going to come right back to it. But I had to get in just a description of impulse. Now, sometimes we say a person has impulse control problems. We don't really mean the same thing here. Impulse in physics is a fancy word that means the net force multiplied by the time over which it acts. Of course, if you look at that equation, what is the net force multiplied by the time over which it acts always equal to? The change in momentum. So impulse is a word that really means change in momentum. When people use impulse, they use it to mean, okay, so what was the change in momentum caused by a force acting on something? Now, you might have had a reading quiz question about airbags in an automobile. Automobiles have lots of safety features. One of them is seat belts. So back in the day, you had a car with seat belts and you felt really safe. The seat belt was bolted to the frame of the car, bolted to the frame of the car, and you had this belt going across you. And if you got in an accident, it would keep you from flying forward and hitting the steering wheel. The problem is, it basically was cutting you in half, right? And it acts as a fulcrum. If you start going forward and somebody stops your waist, what happens to your head? It goes faster, so you go wham! It's like when I was an EMT, my first ever ambulance run. A dude who'd been tweaking for 3 days, he fell off a ladder, hurt his back, went to drive to his mother's house so she could take him to the emergency room because he didn't have a driver's license. Go figure. On the way, he fell asleep and hit a tree. He had to drive 5 miles. Fell asleep, hit a tree. And of course, he didn't even have his seatbelt on. So what's supposed to happen to him? Well, we know the law of inertia, Newton's first law. An object in motion stays in motion unless a force acts on it. So the car stopped, but he didn't have a seatbelt on. Friction's not that big. So he flew forward on his seat because he didn't have a seatbelt on. And of course, his chest was stopped by the steering wheel, and his melon was stopped by the windshield. And he essentially kissed the windshield. And so my job actually was to try to keep blood out of his eyes. And I wrote on the patient care report, PCR report we have to do after every call, nose was not definable. You could not tell that this man ever had a nose. Just flat. Okay, that's what happens if you don't wear a seatbelt. So the seatbelt is going to keep you from probably hitting your head on the windshield just because you're going to hit your head on the steering wheel instead. Still not great. So then they came up with another option, shoulder strap. Shoulder strap will keep your body from flying forward. It constrains you nicely. So the car stops, you stop with it. Of course, the car stops really fast. So you had a momentum, let's say you're going 50 miles an hour, you've got a mass of 50 kilograms, so you take your 50 miles per hour, get it into meters per second, multiply by your 50 kilograms, and you have your momentum. And when the car hits the tree, how long does it take for the car to stop? Really short, like say 1,000th of a second, 5,000ths of a second, somewhere in that ballpark, really quick. And so you go from having all this momentum to stop in a very short amount of time. According to Newton's second law, that net force is the change in momentum divided by the change in time. So that very short amount of time means your body's change in momentum divided by change in time is a very big number. That force that's acting on your body is really big. So you have a really large force going across your chest. Not pleasant, right? So then they came up with better ideas for safety. The first idea is not the airbag. The first idea is, hey, we got these seatbelts that are bolted to the chassis. How about if we put a spring there? So you have a bolt to the chassis, and then a spring, and then the connector to the seatbelt. Then when you get in an accident, the spring is going to expand, making it so you stop in a longer amount of time. Let's suppose that instead of stopping in 1,000th of a second, you stop in 100th of a second. What's that done to the net force acting on you? Yeah, divided by 10. So that's a lot safer, right? Less force, less things that it's going to break. So nowadays, we have our seat belts that are much nicer than when I was a kid, right? When I was a kid, you didn't have any of that pull it out and snap it on. It was, bolted and bring it over here and then take out the extra space like you still have on airplanes. Because let's face it, the seatbelt in the airplane is only going to help you in turbulence, right? You crash, it doesn't matter. And in turbulence, they want to keep you from kissing the ceiling, and so they lock you in there and you're jerking around, right? So then we have airbags. Airbags are a very interesting thing unto themselves. How do airbags deploy? What's the mechanism that makes them deploy? Explosives. Boom, you have a bomb in your car. And so if you get in an accident, you have a motion sensor that says, ooh, the acceleration is too big. And so I'm going to make the explosive go off. That's what happens. That's why you've seen that Facebook video of some lady slowly getting across the road. Somebody honks a horn and she hits the car with her purse. Has enough acceleration. They're causing enough acceleration for the bumper to trigger the airbag, and the guy gets the shock from the airbag. Because it's explosive. That airbag deploys at about 200 miles an hour. Now let's imagine that you are short. I will pick on Bridget. Bridget, you're relatively short. Because you're relatively short, you probably sit relatively close to the steering wheel. And American cars have, most cars, I say American cars because this summer we saw I think it was a Stryker, and made in Holland, and it doesn't have an airbag in the steering wheel. In American cars, it's required that they do. So you have an airbag that's in the steering wheel. And so if you're short, that's close. Of course, the airbags don't know how close you are, and they're set to deploy a certain length, and then they're fully expanded. They're stopped by their own size. If you're sitting close, it's going to hit you at 200 miles an hour, and it can cause damage. So there was, it's been a decade at least now, I think, but there was a lawsuit, and now dealerships are required to disable the airbags if you're short and come in and request it. Because it's dangerous for you for the airbag to go off because it's going to hit you really hard. If you're short. If you're tall, it's not much of a problem because it's going to deploy before it hits you and stop before it hits you. So it deploys 200 miles an hour, comes out here. The backs of those airbags have big cutouts, big holes. Why? So they will deflate quickly. So the idea is it comes out here and stops, you hit it, and then it deflates, and it'll deflate quickly, but it's still a lot longer time that's pushing on you than it would have been without. Question here?
How short is short?
I don't know. It is always something to look into. You can't have kids riding in the front of a car anymore because airbags are dangerous for them, right? That's why you can't have children riding in the front of the car. That's the back seat. But it's safer for most people having the airbags. So the whole point of all of these safety things, from the seat belt with its springs to the airbags, is to increase the time when your body stops, hence lowering the net force acting on your body. That's the whole purpose, and they're effective at it. So these things will help save your life unless there's some crazy situation, in rollovers, being ejected is dangerous, but sometimes not being ejected is even more dangerous. Generally speaking, you're best served to be wearing your safety devices. So when I drive, I always say to my grandson, buckle up for safety. Okay. This diagram here is showing how you might treat hitting a tennis ball with a tennis racket. When you hit the tennis ball with the tennis racket, you have a force applied to that ball that's not uniform. When the ball first hits the strings, it's a small force. As you come through, the ball goes back further into the strings. It's a bigger force. It rebounds. And so your force profile when you hit the tennis ball looks something like that curve. If you want to find the total impulse given to the ball, that is the total change in momentum it's going to have, you need to find the force multiplied by the time all the way through this. Now, we've seen this many times, 3 times counting this. Force net times change in time. If you graph the force net as a function of time, how do you find force net times the change in time? It's the area under it. Yes, you integrate, but it's the area underneath. And so the area under this curve is going to be the total impulse. Of course, even with calculus, I don't have a function for that. I can't solve it. And so a way that you can try to approximate is try to find the average force over the time. And so that's what the rectangle is. Let's find the average force over the time. So you take that shape and just try to find where the average is. Say it's here, boom. And then you can find the actual impulse, which is the change in momentum. Now, of course, when a tennis ball is coming in and you hit it, its momentum started going this direction. I hit it, and it came out going that direction. So its momentum change included change in direction. It could leave the racket the same speed it hit the racket, but with the opposite direction. That's a big change in momentum. Cassie?
I have a question ahead of time for Friday. I'm planning on having homework, and I'm just wondering if you're going to have anything due on Friday during break or not.
No.
Okay.
No. That would not be fair.
I don't know.
Okay. Yes, we always have homework when we have school. We won't have anything during Thanksgiving break either. Okay, what phrase is synonymous with impulse? A what? Okay. Still waiting for 2. Still waiting for 1. Okay. We ended up with a perfect 22 people answered. Change in momentum is what impulse means. Our lab tomorrow, we're going to be dealing with collisions and change in momentum and energy. I didn't get to the slides on those, but we will learn plenty about them tomorrow.